To find out who allocated it, you have to look at the address. If it's on the stack, then you can simply look at the stack frames of all the functions and find out which stack frame it's on. This will tell you which function this variable belongs to. Then you can disassemble the function and see what the variable is used for. If you want to find out who is supposed to initialize the variable, who writes to it, you could use a hardware breakpoint to catch writes to that location. But to do that, you need to send a non-exploit request, because if this is an uninitialized variable exploit, then nobody writes to the variable. So you have to modify your exploit to make it safe, to send a safe request that will trigger the initialization code, and then your write breakpoint will catch that initialization. If the variable is on the heap, then again it's a little bit more complicated. To find out who allocated this variable, you have to find out who allocated the heap block, and for that you can use the techniques from the previous slide. Finally, the most fun ones. If you have non-memory corruption vulnerabilities, such as directory traversals or a variety of other issues, you can't really debug them very well with a debugger, because you don't see any crashes, there's no memory corruption, you're not going to get any exceptions. So probably your best bet is to use runtime tracing. I think Process Stalker or a bin Navi might be useful for that. But it's still a hard problem. So if you can, I suggest that you wait for the official patch and then you just see what they fixed. So now we get to the most fun part of the presentation, and this is how to do vulnerability analysis and how to build a hot patch. And we're going to do this in about 15 minutes. Maybe more, if I have to explain more things. The vulnerability that we're going to analyze is the create text range vulnerability, which is cheating a little bit because I know what the answer is, and I've done this before, but I will still try to do every single step. So you can see how, even if the steps are easier because I know what they are, you should be able to see how, if this were a new vulnerability, you can still follow the same process and get the same result, even if it takes you a little bit longer. So we're going to start with crash HTML, which is a, can you see that all right? Okay. We're going to start with crash HTML, which is a little HTML file that crashes Internet Explorer when you open it. And the important things in the file are this input element here, which is a checkbox. And then we have some JavaScript code which calls the create text range method on this element. According to the official documentation, create text range is only supposed to work for elements that contain text, such as text input boxes or buttons, but checkboxes and radio buttons don't have text. What happens when you open this HTML file is a crash in Internet Explorer, and here you get the window that we're all so familiar with. We're going to close it, and the first step of debugging this vulnerability is to open Internet Explorer and the debugger. So we're going to start Internet Explorer. We're going to pass the crash HTML file as an argument to get it loaded. And we'll let it run, and we see a crash. So take a look at the, so the crash is an access violation, it says here, and this is the address where the access violation happened, and it's an invalid address because there are no bytes there. This means that the program jumped to an invalid location, or probably called an invalid location. And to exploit this, you just have to fill the Internet Explorer heap memory with your shellcode. And if you allocate enough space and fill it with shellcode, chances are some of it will fall into that address. And for some reason, we always get that exact address when IE crashes. So if you have shellcode there and IE jumps to that location, it'll execute your shellcode, and we've exploited IE. But what we're interested in now is what causes the vulnerability. So let's look at the call stack. The call stack shows all the functions that were executed prior to the bad jump. And we're going to look at the last return address on the stack. And hopefully this will get us somewhere. I prefer IDA to WinDBG for looking at disassembly, so we're going to open MS-HTML in IDA. This will take only a few seconds. Bear with me. All right, so this is MS-HTML. Can you see this all right? I guess so. So we'll go to that address. This is the last return address on the stack, and we see a call instruction which dereferences ECX and jumps to it. So possibly this is the call instruction that jumped to the invalid memory location. To confirm this, we're going to look at the ECX register and the memory that it points to. And we see that it points to the first word in the memory is this 3C0474C2, which is the same place where we crashed. So this confirms that this call instruction jumped to the invalid memory. So what does this instruction do? If you've done any C++ reversing, you'll recognize this as a virtual call. ECX is supposed to point to a virtual table, and here we're calling the first function in that virtual table. So if ECX is the virtual table, then EDI must be the pointer to the object, because the first D word in the object structure is a pointer to the V table, and here we assign that into ECX before we do the call. So let's look at where EDI comes from, and we're going to switch to the IDA graph view because it makes things more clear. So we're interested in EDI. EDI comes from dereferencing EAX, but EAX comes from arg14, which is one of the function arguments. And from looking at it, we see that probably this function argument is a pointer to a structure, and the first field in the structure is the word 9, and then we add 8 to it. So the field at offset 8 in the structure must be our pointer to the C++ object. So the next step is to look at every place where arg14 is used in the function and make sure that it's not modified. And I'm going to skip that because it's tedious, but trust me, arg14 is never assigned to in this function, so it does come from the arguments that were passed to it. And here, if we look at arg14 in the arguments, it is the 1, 2, 3, 4, 5. It is the 6th argument of the function. So if we look at the function prototype, because it's a C++ function, the first argument it's an std call C++ function, the first argument on the stack will be this pointer. So arg14 would correspond to the 5th argument in the prototype, which is this thing. It's a pointer to a variant structure. And the variant structure is actually defined in one of the Windows header files. It is used for passing values around between JavaScript functions. It contains its first element, which we saw was 9 in this case, is a type identifier, which tells you what type of value is stored in the variant. And it can be a string, it can be an integer, a number of other things. 9 means VT dispatch, which indicates that the variant structure contains an object pointer. So it all seems to fit. And the object pointer, if we look at the definition of the structure, the object pointer would be at offset 8 in the structure. So now we have to find out where this variable comes from. And we know that EAX points to the object pointer. So EAX minus 8 will be our structure. So this is the variant structure. The first word here is 9, and then this D word is the object pointer. So if we look at the address of it, and we compare it to ESP, we'll see that they're very close. So this structure is located somewhere on the stack. Let's look at the call stack again. And the first column in the call stack shows us the frame pointer of each function. And if we look at where the address of the structure fits, we'll see that it belongs to the stack frame of this function, which is C script runtime run. So this means that the run function allocated this variable on its stack. So let's look at and it's located in JScript DLL. This is actually the location that EI patched. Let's look at the JScript file. So this is the C script runtime run function. And if we subtract this address from the address of the stack frame, we'll get the offset of that local variable, and it corresponds to var 70 because the difference between the stack frame and the variable is 70 bytes hex. And we see that var 70, we take the address of var 70, so we take the address of the structure, and then we pass it as the fourth argument of this function, which is invoke by disp ID. And looking at the call stack, we see that yes, invoke by disp ID is what the run function called to follow that path that led to the crash. So now that we know who allocated this variable, we need to find out whether the variable was left uninitialized, causing the crash, or if the variable was overwritten. So to do this, we're going to restart Internet Explorer. We're going to put a breakpoint at this place here, right where we take the address of the variable, and we're about to pass it. We let it run. And actually, this breakpoint will be hit twice, and the second time is the one that leads to the crash. Here we have the address of our structure. Here's the structure. We're going to put a hardware breakpoint that catches all writes to the third D word of the structure, which is the object pointer. So we want to find out if that object pointer ever gets overwritten. Put a breakpoint, run it, and the breakpoint doesn't hit. What does this mean? It means that the object pointer was never written to before the crash happened. So most